And there is one more application, not necessarily for data science projects, but for mathematical modeling in other applications. So that is diagonalization. So right in the beginning I said eigenvalue decomposition will help you write the matrix A as a product of three matrices, in which the middle one is actually diagonal. So suppose I want to write A as some matrix S and some matrix which is completely diagonal, so lambda and S inverse. So I'm reusing the letters S and lambda, so it's got something to do with the eigenvectors and eigenvalues. So if you can write it in this form, this is actually a very good situation to be in any kind of chain or difference equation kind of modeling of a system. So if you describe the system as a vector and you say that at every step, at every iteration, the system changes by a matrix multiplication, it changes into something else. So at step 0 you have x0, at step 1 you have x1. I have some system and it is fully described by a vector x0 which has got a large number of components, measurements of the system maybe, and that is at time t0, time instant or time sequence number t0. And in order to get x1, that is going to be ax0, suppose that is x1. So evolution of the system is modeled by the matrix multiplication A, and which depends only on the previous state. And if I want to get x2, then that will be ax1, that will be x2, which is the same as a squared x0. So you have to square the matrix. This kind of modeling, by the way, in which the state of the system depends only on the previous state, nothing beyond that, the memory is only one step, that is called a Markov chain kind of modeling. So there's another model called hidden Markov model, which is also based on this kind of idea, and that is used in text analytics, in parts of speech, tagging of words, etc. So what I'm trying to say here is, if you keep going, suppose you want to know xk, that is basically going to be equal to a to the power k x0. So you may need to take powers of the matrix. Now, if you can write the matrix in this decomposed form, taking a square will mean multiplying this twice, and in between what you have is S inverse S, which becomes I, so that disappears, and then you have lambda square. Lambda square is a lot easier to compute compared to a square, because lambda is a diagonal matrix, and the square, you just take the diagonal elements and square it. So a to the power k will be just two matrix multiplications and an exponentiation of the diagonal elements of one matrix, so which is a lot easier to do than multiplying a k times. Without diagonalization, if A is an n by n matrix, the best algorithm we have to do the multiplication, the complexity is of the order n to the power 2.3. And if I have to do it k times, then it's k times n to the power 2.3 operations. That is what you will need. With diagonalization, it takes only two matrix multiplication, so that costs me 2 times 2 n to the power 2.3. And then I have not k but n exponentiation, because I have n elements in the diagonal of lambda. I have to raise each one of them to the power k. Let me call that n operations. Then that total is n plus 2 times n to the power 2.3. And if you compute the saving, you will see that it is actually k by 2. If I want to take, say, 100 power of it, I save a factor of 50 in that operation if I had diagonalization. So if I would take, say, 50 minutes to compute the multiplication, it will take only 1 minute to compute the same thing using diagonalization, plus maybe a little bit of time to actually do the diagonalization, but that's negligible. So that is a kind of thing that you can get by diagonalization, in specifically from the perspective of computer science, savings in terms of computational complexity. So why take powers? It's a common technique in difference equations and Markov chains that I just described. In fact, we can define exponentiation of matrices through Taylor series expansion, and that is actually used in solving differential equations, but that's not part of this course. So difference equation that I showed you just now basically says that the kth state depends only on the k minus 1 state through a matrix multiplication, and if I expand it, xk actually depends on the original state x0 by a to the power k, which we can actually use our diagonalization to compute very easily with the saving of k by 2 operations, a factor of k by 2. So it's a common method to model mathematically using difference equation, and which are computed iteratively. So that much for the motivation. What we do is we start with the eigenvalue equation, a times si, is equal to lambda I times Si. So Si is an eigenvector of A with the eigenvalue lambda I. So that is the statement there. And suppose I arrange all these eigenvalues in a matrix S as columns, then I go ahead and arrange all the eigenvalues as the diagonal elements in another matrix, a square matrix, n by n matrix, like that. If I do that, then suppose I compute A times S. So A times S will be A times the matrix S, which has columns S1, S2, S3 standing there. And as you know from the block multiplication from the first chapter, that is basically distributing A inside and applying it to each one of the columns. So I'll get AS1, AS2, A up to ASN. But Si is an eigenvector of A with the eigenvalue lambda sub I. So I'll get lambda 1 S1, lambda 2 S2, lambda I Si, lambda n Sn. Like that. So that is one side. Let me call that the LHS. Now if I look at the other side, suppose I take S times lambda. So S is just the vector S1, S2, S3 up to Sn, and I have lambda, which is a diagonal matrix. If I do the multiplication, what will happen is something like I have S1, I'll just take two eigenvectors, that is my S matrix, and my lambda is a lambda 1 and lambda 2 and 0 here, 0 here. In order to get the first column of the product, I'll take lambda 1 times the first column and 0 times the second column. So that product will become lambda 1 S1, and the second one, similarly, I'll take the 0 times the first column and lambda 2 times the second column. I'll get lambda 2 S2. The product S lambda, if I extrapolate that to n vectors standing side by side, is the same as a matrix with lambda 1 S1, lambda 2 S2 up to lambda n Sn standing side by side. So that's what I wrote there. So S lambda is lambda 1 S1, lambda 2 S2. If I compare that with AS, which also is the same thing, so this guy is the same as that, then you can see that they are the same. So I can say confidently that AS equal to S lambda. So AS equal to S lambda. That is always true, regardless of how many eigenvectors you have, what algebraic multiplicity is, and geometric multiplicity. All those things are irrelevant, because whatever we did not make any assumption. AS equal to S lambda is always true, which means if I multiply both sides by A again, what will happen on this side? AS is equal to S lambda. I put S lambda there, and I multiply by A again, and I get A square. And then on the other side, lambda just gets square. So A to the power k S is equal to S times lambda to the power k. That also is always true. Now, if I make an assumption that S is invertible, what that means is that we have n linearly independent eigenvectors. If that is the case, then I can take S to the other side. I can multiply both sides with S inverse. AS is equal to S lambda, always true. But if S is invertible, I can multiply both sides with S inverse, or AS S inverse is equal to S lambda S inverse, and this guy becomes I, and that just goes away. So A is equal to S lambda S inverse, and which was the decomposition that we're looking for. So that decomposition is possible if S is invertible. So if you can find the linearly independent eigenvectors, then you can write that. But if you can find linearly independent eigenvectors, then you can use that as a basis also. So there is a nice basis called the eigenbasis. So any vector in Rn, because I have n linearly independent eigenvectors, can be expressed as a linear combination of the eigenvectors. So if I call that linear combination with scalars Ci, then I can see that x0 is actually just the matrix S times C, which is a vector. So that vector C would be the vector x0 expressed in the eigenbasis. Why would you want to do that? Because the difference equation xk, which is the kth state of the system, was a to the power k times x0, and if x0 is actually sc, then a to the power ks, as you can see here, is just s lambda to the power k, so it just becomes that, which is easy to compute. This guy is hard to compute, but this guy is very easy to compute. So the diagonalization is a process of getting A in this form, and this, since it is a decomposition, a factorization, this is also called eigenvalue decomposition, or EVD for short. That is a pretty interesting and very useful decomposition. Now let's look at one fun application of eigenanalysis. So it's the Fibonacci series, the Fibonacci sequence of numbers. It happens in nature all the time in terms of the spirals and spirals going in opposite directions or stuff like that on pineapples and sunflowers and all that. Okay, so that is a Fibonacci sequence, and it's got very interesting properties. Interesting sequence is very easy to compute. K plus 2 element is the sum of the previous two, k plus 1 and the kth elements. Sum them up. It is, if you think about it, it's like a Markov chain. Instead of depending only on the previous step, it depends on two steps. So it's a second order difference equation if you want to be very formal about giving it the right name. Now the question that you might ask ourselves is, how fast are these numbers growing? These numbers are obviously growing. It's 1, 1, 2, 3, 5, 8. And it doesn't look like there is any clear way in which you can compute how fast these numbers are growing. And even more impressive, can you come up with an approximation for the kth Fibonacci number? That also doesn't look at all obvious here. But eigenvalue decomposition, the eigenanalysis, will tell you that it is actually possible. Of course, in order to do anything to do with eigenvalues and eigenvectors, obviously you need to have a matrix, and we don't have any here yet. So we will create first order matrix equation. So a second order difference equation will become a first order matrix equation. Let me consider a vector which has two elements, a Fibonacci number and the previous Fibonacci number, k plus 1 and k. And if I do that, then if I want to compute the next vector, that is x sub k plus 1, so wherever I see k, I'm going to put k plus 1, so k plus 1 plus 1 and k plus 1 here. So I get that. Now I get fk plus 2 as the first element, but I know that fk plus 2 is fk plus 1 plus fk. So I put that in there. Then suddenly I can see a matrix there. I can see that the k plus 1 state, that vector, is actually the kth vector times a matrix. Now that is my matrix A. It's 1, 1, 1, 0. And then I can go ahead and do the eigenanalysis. I write the characteristic equation, A minus lambda I, the determinant of, and I get that, and expand out the determinant 1 minus lambda times minus lambda minus 1, and do a bit of basic algebra. Then I get lambda square minus lambda minus 1 equal to 0. That quadratic equation is just about the most famous quadratic equation in the world, the most significant one. But before telling you why that is the case, let's compare that equation, lambda square, lambda and 1, coming with minus signs there, and compare it to our second order equation there, and take everything to one side. So fk plus 2 minus fk plus 1 minus fk. So k plus 2, that is second order, k plus 1, that is first order, k, that is the 0th order, and the right sign and right coefficients. So that is actually the characteristic equation, actually captures the essence of the Fibonacci sequence. From the properties of eigenvalues that we talked about, some of the eigenvalues of the matrix A will be the same as the trace, which is, what is the trace here? 1. And the product will be the same as the determinant. What's the determinant here? Minus 1. But we have the characteristic equation, and this is a quadratic equation. We know how to solve it. So I just solve it. You will get lambda is equal to 1 plus or minus square root of 5 divided by 2. That number again is actually a very famous one, especially the positive one. So lambda 1 is 1.618, and that is actually the golden ratio. 1 plus square root of 5 divided by 2. Golden ratio, again something that appears in all kinds of aesthetic kind of stuff like paintings, architecture. Has got very important properties in terms of how we perceive things apparently. But as you will see, it is also significant in terms of Fibonacci numbers. So there is a connection between Fibonacci numbers and this golden ratio, which is interesting. So lambda 1 is actually the golden ratio. Now, the absolute value of lambda 1 is more than 1. The absolute value of lambda 2 is less than 1. So the statement I'm going to make is that the sequence is going to grow as lambda 1, because that is what we call the dominant eigenvalue, because that is the highest in terms of absolute value, and it is more than 1. So the system is actually going to grow exponentially, and the growth rate is going to be 1.618. So that means if I take the 100th Fibonacci number divided by the 99th Fibonacci number, that ratio is going to be very close to lambda 1. That is my statement. In order to see why, we will have to look at the vector that we constructed, which had, remember, fk plus 1 and fk. We can express that in the eigenvector basis with some coefficients. We don't really need to know the eigenvectors yet. We just need to know that it can be expressed. I have two eigenvectors. They are orthogonal to each other, and I can express any vector. In particular, I can express x0, which was just 0, 1, I believe, or 1, 0 rather, in terms of the eigenvectors. And then I know that xk is going to be a to the power k times that x0, which means it's going to be c1 times a to the power k s1, c2 times a to the power k s2. And since s1 and s2 are eigenvectors, I know that a to the power k s1 is the same as lambda 1 to the power k s1, and the second one is lambda 2 to the power k s2. So this we already saw. Now look at lambda 1, that absolute value is more than 1. Lambda 2 absolute value is less than 1. So as k grows, as k becomes like 10 or 15 or 100, this guy is going to just disappear, because lambda 2 to the power k is going to be a very small number. But lambda 1 to the power k, on the other hand, is going to be a large number. So we can ignore this guy, and we can say, regardless of what s1 is and regardless of what that coefficient is, we know that xk is going to grow in accordance with the dominant eigenvalue. So xk is kind of similar to that which grows as the dominant eigenvalue. If you want to actually know what exactly that Fibonacci number is as an approximation, the Fibonacci numbers are going to grow as the golden ratio, which means the 100th Fibonacci number divided by the 99th Fibonacci number is actually going to be the golden ratio, 1.618 whatever. But if you want to actually be able to compute the 100th Fibonacci number as an approximation, then we need to find the eigenvalues and eigenvectors. Eigenvalues we already have, but we need to know the eigenvectors, and we need to express x0, our starting vector, the starting state vector, in terms of the eigenvectors, in the basis of eigenvectors, in the eigenbasis. We can actually see that the eigenvectors s1 is lambda 1, 1, and s2 is lambda 2, 1. That is easy to see. Okay, so this is what I want to do. If I take s is equal to lambda and 1, what do I get? I get lambda minus lambda square plus 1 in the top, and in the bottom I get lambda and minus lambda. And the second element is obviously 0. The first element is actually the characteristic equation. Remember, our characteristic equation was lambda square minus lambda minus 1 equal to 0. Multiplied by minus 1, you get the top one, so that also is equal to 0. Eigenvectors are of the form this, so I have lambda 1, 1 as 1 eigenvector, I call that s1, and lambda 2, 1 as a second eigenvector, I call that s2. We know that the approximation for xk is whatever linear combination we have for x0, and we ignore the second term there, s2 is ignored because that is going to be multiplied by lambda 2 to the power k, and so we need to worry only about s1. And if I do all the multiplication out and expand it, I'll get fk plus 1 is equal to c1 lambda 1 to the power k plus 1. Fk is equal to c1 lambda 1 to the power k. And obviously fk plus 1 divided by fk is of course lambda 1, which is the golden ratio. But as you can see, fk is just c1 lambda 1 to the power k. So we need to find c1 also. And then we have an approximation for fk, c1 lambda 1 to the power k. So what is c1? In order to get c1, we look at x0, and that is 1, 0. So the first Fibonacci number is 1. The 0th one is 0 in our sequence. And we express that as a linear combination of the eigenvectors. So I have that. And that basically gives me two equations. C1 lambda 1 plus C2 lambda 2 is equal to 1. That is the first one. And C1 plus C2 is equal to 0. That is the second one. Two equations, and we know we are experts in solving equations of that kind. And so I'll get C1 is equal to 1 divided by square root of 5. So fk, the kth Fibonacci number, is 1 by square root of 5 coming from C1, and lambda 1 was the golden ratio to the power k. So I have an expression there for the kth Fibonacci number, a numeric expression, which depends only on k. And this is actually surprisingly extremely accurate. By the time you reach the fifth Fibonacci number or something like that, you will see that the error in the approximation is a few parts in a million. It is very, very accurate. So that is the application of eigenanalysis in something that was a series of numbers, a very famous series of numbers, but a series nonetheless. Of course, this is only an academic exercise, but similar applications can be seen in other kinds of difference equations and how systems evolve. And you will see that the approximation is actually a very